Welcome back everyone. We have already discussed about the phenomena of refraction, that is bending of light at the interface of two media. We also discussed about the refractive index that measures this extent of bending. Today we will see a few practical applications of the phenomena of refraction, and first one is refraction through a glass slab. Now this is a glass slab. It is a rectangular piece of glass which is thicker. Now if we pass light from one side of the glass so that it passes through the glass and then comes out from the other end, we can see that here refraction occurs two times. First, light from air enters into glass, rarer to denser medium, so it will bend towards the normal. Then from glass it comes out again into air, now from denser into rarer medium, and it bends away from the normal. So these three rays are called as incident ray. Inside the slab it will be refracted ray, and the ray that comes out of the slab back into the air will be called as emergent ray. This experiment can be performed in the laboratory by taking a glass slab and keeping it on a white sheet of paper. After that we will make the boundary wall of this glass slab and draw an incident ray and normal, taking care that the angle of incidence should be between 30 to 60 degrees. After that we will take two pins and insert these two pins along the incident ray, making sure that the distance between the two pins is at least 3 to 4 centimeter. So now we'll insert the two pins along the incident ray, and we take a third pin and go on the other side of the slab and look through the slab at these two pins. And then we will insert the third pin in such a manner that all three pins appear to us along the same straight line. Then we will take a fourth pin and insert this pin also in such a manner that all four pins appear along the same straight line. Then we remove the pins and join the marks made by the two pins. Join them with each other and then join them with this glass slab. Now we'll remove the glass slab and all the pins. So we have made this emergent ray, and this was our incident ray. So we know that incident ray is entering the glass slab here and it is coming out of the glass slab from here. It means that this ray has bent along this path, which will be our refracted ray. So now we have made three rays: incident ray, refracted ray, and the emergent ray. We will show the refraction through a glass slab with the help of this diagram. For that, first of all, we'll draw the boundary wall of the glass slab, and three rays, incident ray, refracted ray, and emergent ray, we will draw. And these two interface between air and glass, we'll draw a normal, and then from between glass and air, again we will draw a normal at this interface also. We need to mark three angles very carefully. Angle between incident ray and normal is angle of incidence. Between refracted ray and normal is angle of refraction, and between emergent ray and normal is the angle of emergence. We will also extend the incident ray in dotted lines up till here. From this experiment, we will make four very important observations. Now, our first observation is that incident ray is parallel to emergent ray. So we have extended this incident ray and this is our emergent ray. We can see these two are parallel to each other. Second observation is that angle of incidence is greater than angle of refraction. It is obvious because this ray has bent towards the normal, so angle of refraction is smaller. Third very important observation: angle of incidence and angle of emergence are equal. If these angles come equal to each other, only then our experiment is correct. This was the original path of the incident ray, but when the ray comes out of the glass slab, it comes out from here. So it has been displaced to one side, and we call it as lateral displacement. So in this case, there is lateral displacement, which is also called as lateral shift. While performing this experiment, we need to take a few precautions. First precaution is that angle of incidence should be between 30 to 60 degree, because if the angle will be less than 30 degree, then we will not be able to make all these observations clearly. And if it is more than 60 degree, then rays will come out from this side and the results will not be clear. Second important precaution is that when we insert the pins in the incident ray and along the emergent ray, the minimum distance between the pins should be 3 to 4 centimeter. Another precaution is that when we are looking at the pins from this side of the glass slab, we have to look at the feet of the pin and not at the head of the pin. So we'll be looking at the feet of the pin while keeping all the 4 pins along the same straight line. And while observing the pins from this side, our eye level should be at the level of the glass slab or at the level of the pins. So we have to bend down to see the pins. So these are the 4 precautions that we'll be taking while performing this experiment. We will now learn the technique to draw this diagram in a stepwise manner. First of all, we'll draw the outline, boundary of the glass slab, make the incident ray and the normal. Extend this incident ray in the dotted lines up till here. After that, we will first draw the emergent ray. And emergent ray should be parallel to the incident ray, slightly towards one side, and parallel to the incident ray, we will draw this emergent ray. Connect emergent ray with the incident ray to form the refracted ray and draw normal at this interface. After that, we will now show the path of the rays with the help of arrows and mark all the angles carefully. So this is the angle of incidence, angle of refraction and angle of emergence. We need to draw 3 angles. All the 3 angles are with the rays and the normal. We will now mark the rays, incident ray, emergent ray and the refracted ray. 3 rays we need to mark. And this distance is the lateral shift. It is the perpendicular distance between the incident ray and the emergent ray. And these are the 4 observations that we will make in this experiment. Now we see that there is lateral shift or lateral displacement. Now we want to know on what factors this lateral shift depend. When will this lateral shift be more and when can this be less? So let's see those factors on which it will depend. These are the four factors on which lateral shift depends. First is angle of incidence. More the angle of incidence, more will be the lateral shift. More the thickness of the glass slab, more will be the lateral shift, and more the refractive index of glass, more will be the lateral shift. But if wavelength of incident light is more, in that case, lateral shift will be less. Another example of refraction of light is that a stick partially immersed in water appears bent at the interface. Remember this activity that we performed earlier. This pencil is appearing bent at the interface when it is immersed in water partially. The same is here. Now we will understand this concept with the help of this ray diagram. Now this stick which has been immersed in water partially, half of it is inside water and rest half is in air. It is appearing bent here. Now the reason is the rays of light which originate from this part of the stick, when they reach the interface, now they will move from a denser to a rarer medium. So they will bend away from the normal and they will reach our eyes. But our eyes cannot perceive the actual origin of the rays because it cannot perceive the bent path. It can only perceive the straight line path. So if we extend these 2 rays backwards, they appear to come from this point. For our eyes, this part of the pencil is here. As a result, this pencil or the stick appears bent at the interface. Now we will learn to draw this diagram in stepwise manner. First of all, a stick half in water and half in air, and then we will show the bent path of this stick here. Make this angle large, approximately 50 to 60 degree, and the length of this bent part I have made half of this part which is inside the water. Now we will start a ray of light from this bent part. Up till the interface it is dotted, and after the interface it has been a complete line. We will start another ray from the same point, and up till the interface dotted, and after that it will be a complete line and the 2 rays will be diverging. Now we will start from a point here and connect it with this point. Another ray from the same point and connect here. And we will show the direction of the rays with the help of arrows. Draw the normal at the 2 points of incidence, and we are looking it from here. So make an eye here. So this is our diagram, which is showing that a stick partially immersed in water appears bent at the interface. Another example, a coin appears raised when immersed in water. If we place a coin in an empty container, it will appear here. If we fill the same container with water, the coin which is actually here appear here to our eyes. Now the same concept is applicable as in the previous example. The rays of light which start from this coin, when they reach the interface, they bend away from the normal and reach our eyes. And as our eyes cannot perceive the bent path, it can only perceive the straight line path. So on extending these rays backwards, they appear to come from this point. So instead of here, coin appears here to our eyes. This is the actual or the real depth of the coin, but it is appearing here. So this will be the apparent depth of the coin. From these two values, we can find the relative refractive index of this liquid. If it is water, then we will find out refractive index of water with respect to air, which will be equal to real depth upon the apparent depth. Now the steps to draw this diagram. We will first show the coin at the bottom and at certain height also. From here we will draw two lines, two rays from the same point. Up till the interface they should be dotted, and after that they should be complete lines and they should be diverging from each other. Now from one point here we will draw two lines joining at this point and at this point. So another ray at this point. Now these are the rays, so we'll show the direction of the rays and label the diagram and draw the normal at these 2 points also. And this formula will give us the relative refractive index. I hope now you have understood this concept and the method to draw the ray diagrams. So let's see one more example. A swimming pool appears shallower than it actually is. So the same concept, the rays of light which start from the bottom of the pool, when they reach the interface, they bend away from the normal, and to our eyes, they appear to come from this point. So as a result, bottom instead of here appears here to our eyes. Now the technique to draw the diagram, we will start from a shallow part, two rays from the same point, and these two rays should be diverging. We'll draw normal in both the rays. Now this bottom is appearing here also. So we'll start from the actual bottom and draw two rays, one connecting here and other connecting at this part, and show the direction of the rays. Now here also, this is the actual depth of the pool and this is the apparent depth of the pool, and using these two values we can find the relative refractive index of water with respect to air. Now these are few more examples, some we have already discussed, some we have not discussed. So you can note down these examples. One example is a lemon appears bigger when kept inside the water. Remember, this activity also we have already performed. So it is looking oval also and bigger also, though both the lemons were of same size. Similar concept is for oval shape of sun at sunrise or sunset, twinkling of stars. Letters appear raised when a glass slab is placed over some printed material. So these are few examples for refraction phenomena. And that is all for today.